Action potentials of ventricles, atria, and Purkinje system. These are the 99% of the heart's muscle cells. The cardiac muscle cells reach threshold as a result of receiving action potentials that travel through the conduction system or through the gap junctions that are connected to these tissues. The ionic basis for action potentials inside the ventricles, atria, and Purkinje systems are identical. They have three key characteristics: a long duration, the action potential can vary. In the atrias, it's about 150 milliseconds. The ventricles is about 250 milliseconds, and the Purkinje fibers is about 300 milliseconds. In comparison, skeletal muscle has an action potential of about 1 to 2 milliseconds. These longer action potentials means that the cell must have a refractory period before firing another action potential. Atrials, ventricular, and Purkinje cells all have long refractory periods. There's also stable resting membrane potential. The cells inside these structures exhibit a stable, constant RMP. There's also a plateau phase in which the action potentials of the cells are characterized by a flat line. This is sustained ability to maintain depolarization. Let's take a look at each of these phases. The first phase is called phase 0, also referred to as upstroke in the action potential. Again, this happens inside the ventricles, atria, and Purkinje cells. The upstroke is the initial upward deflection of the action potential as it begins to rapidly depolarize. There is going to be an increase in the sodium conductance expressed as G subscript Na. This is produced by depolarization-induced opening of activation gates of the sodium channels. G subscript Na increases due to the inward flux of sodium, causing the cell inside to be more positive. The influx of sodium into cell creates a current, what we call I subscript Na. The potential is then depolarized to a value of roughly about positive 20 millivolts. dV over dt is expressed as the rate of change of membrane potential as a function of time, and this is expressed as volts per second. dV over dt is greatest when the resting membrane potential is the most negative or hyperpolarized, because you have a number of channels that could potentially open up. dV over dt is lowest when the resting membrane potential is less negative or slightly more positive. So roughly about negative 60 millivolts, there's a low dV over dt, and then when you have a negative 90 millivolts, it has the greatest dV over dt. Phase 1 is what we call initial repolarization. Inactivation gates of sodium channels close, and now there's an outward efflux of potassium. The potassium conductance, also referred to as G subscript K, is high. Potassium's efflux out of the cell. This then quickly leads to the phase 2, the plateau phase, which is a long period ranging from 150 to 200 milliseconds, depending on what type of structure we're referring to. And there's an increase in calcium conductance. So the G sub Ca begins to increase. This then leads to a phenomenon that we'll revisit called calcium-induced calcium release, as there is an inward flux of calcium current that triggers the L-type channels to begin releasing more calcium from the intracellular sarcoplasmic reticulum, leading to contraction. Phase 3 is referred to as repolarization. This combines the decrease in the G calcium and the increase in G potassium that then leads to the phase 4 resting potential, or also known as the electrical diastole, where you have a sum of all the inward currents carried by the sodium and calcium, which is then equal to the outward flux of potassium. This is basically the repolarized to the hyperpolarized state of an action potential. Let's summarize these key electrical events inside the cardiac muscle action potential. So 3 key events occur. You start off by a quick depolarization. This is a result from the gap junctions opening these fast-gated sodium channels. Sodium rushes in, goes from negative 90 to positive 30. Plateau phase is when you depolarize, opening potassium channels, and you also enable these slow voltage-gated calcium channels to open up. Potassium leaves and calcium enters and maintains a plateau phase. That then leads to calcium-induced calcium release contraction mechanism. And then the final part is repolarization, where the voltage-gated calcium channels close, sodium channels are closed, and potassium remains open, and it recharges back to negative 90. So you start off with the fast-gated sodium channels opening up. That's depolarization. So in the plateau phase, you have potassium flowing out of the cardiac muscle cell and slow voltage-gated calcium channels being open. Calcium ions go in, And there really isn't much of a change to the electrical charge, but the depolarized state is maintained. So you can see over here on the graph that you have this sloping downwards that's not flat, but it maintains a fraction of a second. Then repolarization occurs where the fast-gated sodium channels are closed, potassium channels remain open, allowing potassiums to efflux out, and then slowly the voltage-gated calcium channels close down, allowing it to repolarize down back to the RMP. This is a much more simplified way of representing the events inside the ventricles, atrias, and Purkinje action potentials. The nodal cells in the SA node and the AV node have some common features. The SA node physiologically initiates the heartbeat and thus is naturally the dominant pacemaker of the heart. Nodal cells, like neurons, have NAK pumps as well as sodium channels, potassium channels, and they're able to maintain that RMP. The SA node has a few characteristics. It exhibits automaticity, which means that they're capable of spontaneously depolarizing and firing action potentials without any external influence. It also has a relatively unstable resting membrane potential, and there is no sustained plateau phase in this potential. It starts off with phase 0, also the upstroke. This isn't as rapid or as steep as the other cardiac tissues, but there is an increase in calcium channel, and therefore calcium ions go in, triggered primarily by both the L-type, long type, and also the transient type, T-type calcium channels inside the SA node. There is no phase 1 or phase 2 during this part of the action potential. It jumps directly to phase 3, where it will begin the repolarization, in which the GK, or the outward efflux of potassium, begins to take over and repolarize the membrane. Phase 4 is what we call the spontaneous depolarization, or the pacemaker potential. This is what accounts for the automaticity of SA node cells. This is the opening of sodium channels and an inward flux of sodium current, what we call the funny channel. This is also known as the I subscript F. This is different than the fast sodium current channels in the other cardiac cell types. Clinically, if you were to increase the phase 4 speed of depolarization, it will then be able to reach threshold much faster and therefore increase your heart rate. Summarizing the key events here is that it exhibits the autorhythmicity, which is spontaneous firing. The first part is the reaching the threshold. So the slow voltage gated sodium channels open up, sodiums flow in. Voltage change goes from negative 60 millivolts to negative 40 millivolts. On the right hand side, you can see this image showing you that the slow voltage gated channels open up. Depolarization occurs. This is the fast gated calcium channels open up, allowing the calcium ions to rush in. There jumps the negative 40 millivolts to roughly about 0 millivolts, and then quickly begins to repolarize as the calcium channels close and the voltage-gated potassium channels open up and efflux out. This then reverses back to the RMP of roughly negative 60 millivolts, and the cycle begins again. So if you look at the graph on the bottom, you're going to see that there is no plateau phase. It's characterized by the ability of generating this quick funny potential, reaching threshold, depolarization with the calcium inflow, and then repolarization. This bottom region shown here with the pacemaker potential is what you can control to change the speed of the heart rate. The spread of the action potential. The initial action potentials are spontaneously created in the SA node and are then quickly spread along the cardiac cells to the atrias, primarily through the gap junctions between the cardiac muscle cells. The spreading of action potentials reaches the AV node very quickly, and that AV node has smaller cells and less gap junctions, thus slowing down the action potential from reaching the ventricles too quickly. So it gives it some time to fully expand, fill up with blood, and then contract. Once the action potentials have transversed over the AV node, they're then delivered down to the AV bundle, also known as the bundle of His, where the action potentials quickly descend to the two bundle branches, the left and right side, along your Purkinje fibers. The Purkinje fibers then will connect to the cardiac muscle cells at the inferior region of the heart, and then the action potentials will propagate along the inferior ventricular muscle cells through their gap junctions, and allowing it to simultaneously contract on both ventricles to start at the bottom of ventricles and move upwards. Step 1 is the sinoatrial and atrial myocardium. SA node begins in the upper right chamber, flows down to the AV node with a slight delay. As the action potential is delayed through the AV node, it passes through the AV bundle and then down to the interventricular septum. Step number 3, the AV bundle conducts the action potential to the left and right branches and then down around to the Purkinje fibers of the left and right sides. The Purkinje fibers then spread via the gap junctions and allow the entire ventricles to get a signal, and contraction begins from the bottom upwards. Latent pacemakers. Latent pacemakers are cells in the AV nodes, bundle of His, and Purkinje fibers that also have a slight ability to generate automaticity. These latent pacemakers are not dominant as long as the SA node is healthy and normally working, because the SA node has the fastest phase 4 depolarization, and that's why it sets the heart rate. On the right-hand side, you can see the firing rate. SA node is 70 to 80 impulses per minute. AV node is 40 to 60. Bundle of His is about 40, and Purkinje fibers is only 15 to 20. There is a phenomenon called overdrive suppression. This is when the SA node drives the heart rate, and that causes the other pacemakers to be suppressed. However, if the SA node is damaged, or if the vagus nerve is not functioning, or if there is some sort of blockage via diseases, or if one of the latent pacemakers was to somehow get faster, then an ectopic pacemaker would occur. That means any of the other latent pacemakers taking over the SA node's speed.